An electric circuit, I have an example of an electric circuit here. We want to think of it as a closed conducting path. What this means is if we trace a current element through the circuit, we should start at location A, let's say, and end back at location A to complete the circuit. An example we have down here, suppose we start at battery V. Then to complete a circuit, we'd start from the positive terminal, move around. We could get here, we have a couple of options. Let's say we choose this option, pass through this resistor, and then come back to the battery. So any closed conducting path will be considered a circuit. Now we may also refer to this as a loop. So for this particular circuit, we could say, okay, this is a loop through the circuit. This one represents another loop through the circuit. So the minimum condition for a circuit is to close conducting path, but a circuit could be a set of loops, a set of closed conducting paths. So maybe I should qualify this definition here. And we'll say a set of closed conducting paths. And then we'll qualify this definition here for a closed conducting path as a loop. Now, let's see, maybe we'll just say closed conducting path. We'll change this to loop. Let's label a few more elements in my circuit down here so we can talk about it. We'll call this one R1, R2, R3 and R4, within this circuit, one thing I want to be able to do is to identify all of the loops in the circuit. And to identify all the loops in the circuit, I'm going to draw in each of the loops. We'll call this one loop 1, or maybe we won't. Try pen. Alright, let me pause a minute here. Looks like I'm going to use vector arrows to indicate the loops. Oops. We'll call this, let's see, we'll start there. There we go. We'll call this one loop 1. We'll identify a loop 2. Loop is just a closed conducting path. And let's go all the way around the outside. And then for the last loop that I have a loop containing just the 4 resistors. We'll go with, let's see if this purplish sort of color shows up here. Oh yeah, not too bad. Which one did I eat? That one? It's not the same color. There we go. So in this example, we can say that there are 3 loops. In this particular example, meaning 3 closed conducting paths. We'll change that back to black. There we go. And those 3 are loop 1, loop 2, and loop 3. What's important about identifying a loop is we can say that energy is going to be conserved as we pass through a loop. So we'll say energy conservation applies to a loop. What does that mean? Well, it means we better change our color here. There we go. That means that the sum of the voltage drops around the loop has to add up to 0. So the sum of the voltage around the loop has to equal 0. Right? Voltage meaning amount of energy per charge. So if we take a particular charge element and have it pass through loop 1, what we're going to say is we have a certain amount of energy drop associated with the battery, and then a certain amount of energy drop associated with the resistor 1. Those being the only 2 components in the circuit, add up those 2 voltage drops, we should end up with 0. And we'll write that down as our first example here. Oh, there's that red piece. Let's get rid of that red piece. There we go. So for loop 1, what we could say we have is the voltage for the battery plus the voltage for the resistor. We'll call it R1 equals 0. And we can make this equation for each one of the loops, and let's go ahead and do that. So we have loop 2 in loop 2 we have the battery. So let's start with this one. Oops, let's copy it down. Stop doing that. There we go. Copy this down here. And as we pass through loop 2, what we have, we'll start with the battery. We don't pass resistor 1, but we do pass resistor 2. Then we pass resistor 3. Then we pass resistor 4. And then we're back to the battery. Then for loop 3, that's just the inside loop here. We have resistor 3, or I should point to the right one, 3, 4, 1, and 2. Copy this one. And instead of having the battery there, we have voltage from resistor 1. What this constitutes is our first circuit law, conservation of energy, or we could call it Kirchhoff's loop rule. Now there is a sign convention associated with the loop rule, meaning we have to be able to assign plus or minus to any one of these individual components as we pass those. The sign convention will apply to the battery. So for the battery, when you cross it from plus to minus, let's see, a battery, we'll say from plus to minus, we're going to assign that a negative value. And so we'll end up negative V will be what we'll put in the equation. And then of course if we flip that around, it'll be a positive V. Oops, delete. So minus to plus. Be a positive V. Now the other part that we'll be interested in is resistors then. So if we have a sign convention for the battery, we'll need a sign convention for the resistors. Oops, let's change that. There we go. This one's going to depend on the next quantity that we have to identify in the circuit, meaning the circuit current. And we'll draw in two vectors here. So we'll say this one, we'll call it current. A little I is usually what I'll use for current. So if the current is identified as traveling in that direction, let's move the sign convention up here a minute. Alright, got it moved up here. For the resistor portion of the sign convention, if we determine our current's going to flow in to the right, let's say, and then we pass that resistor with the current flowing through it to the right, while going to the left, we'll assign a positive voltage. And then if the current and the loop are assigned to pass in the same direction, we'll assign a negative value to the voltage across that resistor. That takes care of the loop rule. Loop rule is conservation of energy. Right? Voltage times charge gives you energy. So if we took a charge element around the loop, we should say that we, in terms of energy, are back where we started again. The other rule that we're interested in for the circuit is conservation of charge. Conservation of charge relates to the junction rule. So we could say Kirchhoff's junction rule this one is applying conservation of charge to a junction. We better define a junction here. Junction is just going to be the union of two or more components. Let's see, maybe the junction we should say that's a union of three or more components in the circuit. And let me copy our example down from up there. There we go. Have the circuit copied. So now what we want to do is we want to identify the junctions that we have available in the circuit. This one's two connections, two connections, two connections. So those aren't junctions, but here we have three components connected. We have the battery coming in this side, resistor 2 and resistor 1. And so I'll label this one as J1, junction 1. And this one will be junction 2. Oops. Cancel that. Bring this back. Okay, I better stop moving it around. There we go. Back to aligned again. For the junction rule, our sign rule is very nice. In is positive, out is negative. And what I want it to do for the junction rule is I want to assign each branch a unique current. So not only do I need the term of a junction, I also need the term for a branch. A branch is just going to be a conducting path between junctions. In this circuit, notice I have three different branches. One branch contains the battery, another branch contains R1, and a third branch contains R2, 3, and 4. Each of the branches gets labeled with a current value. And you get to assign the direction however you like. We'll call this one I1. So that's my current 1. We'll let this one be I2. And then the last one we'll let be I3. Three branches, three currents. And what I'll do now that I have each of the branches identified with the current, conservation of charge tells me that the sum of the currents at a given junction have to add up to 0. So sum of the current for a junction is equal to 0. I have two junctions, so that means I'll have two different equations that I can write. So I write the whole word out. For junction 1, alright, just a minute. Okay, got my color fixed. Now for junction 1, I have current 1 flowing into the junction. So to start that equation, I have plus I1 because it's flowing in. Then I have I2 flowing out and I3 flowing out. So I have plus a negative I3, or we'll go in order, I2, and then plus a negative I3. And those have to add up to 0. For junction 2, now I have I1 flowing out of that junction, I2 and 3 flowing in. So I have the same equation, but with the signs flipped around. So I have a minus in front of I1. I'll put that one in parentheses now. And then now I can drop the parentheses for I2 and I3. The application of both rules together is that we will be able to solve a circuit. What I mean by solve a circuit, if I can drag, there we go, drag this up. Solving a circuit means to calculate the voltage, the current, the power, or calculate voltage, current, power, let's see, voltage, current, power, and resistance of each circuit component. An easy way to remember this is to put them in a slightly different order and to say that you're going to calculate the perv for the circuit. And perv P-I-R-V. So the power, current, resistance, and voltage for the circuit. What we get is we get an equation for the junction 1, an equation for junction 2. If we scroll back up here, we have an equation for loop 1, an equation for loop 2, and an equation for loop 3. So this gives us 5 possible equations that we can write, meaning that we could have this circuit with at most 5 unknown variables, provided each of these equations is independent. What you'll notice, though, about the junctions is these two equations are not independent. So we would only be able to use one of the junction equations to actually solve this particular problem. And to look at an example, we'll save the example for the next video.